Okay, so now we have written down the theorem. So where it is here. Yeah, here I hope it's readable on the movie. So what we just say that if in a class M and for some historic policy pi, there exists a self-optimizing policy pi, then our special policy pi xi, so that's just takes a mixture of environment, will be self-optimizing. And so the proof is way shorter than the time to explain all the definitions. So let's go over the proof. So I need to delete a few things. So let us first write down what we need to prove. As usual, we want to prove that V, so when we take an environment mu of course inside our model M, and we look to the optimal reward, we want that when we use our policy, special policy pi xi, with environment mu, we want that this goes to 0. And so we want that this with, and then we use mu pi tilde probability 1. Sorry, with, so we, no. So we want this to be true with mu pi tilde probability 1. Oh. Okay, there is a mess. Let's clean it up. We want this, that we want that with probability 1 with mu pi tilde probability 1. And so when history n is given, we want this to go to 0 for n going to infinity. Okay, so first step is we will multiply by coefficient W mu. So recall the definition of xi, it's a mixture over mu's here, and we of course know that mu is in the model. So we multiply by this thing here. And so we want that this, so after multiplying by something positive, convergence with probability doesn't change. Okay, and so now our first step is to bound this. And we will sum over all the mu in the model. So first, so the proof will be two inequalities and a lemma. That's it. And first inequality is nothing. We will just sum over the difference with all other values. So this is bounded by W mu, where we sum over all mu in our model. And so we have mu star of H n minus V pi xi of H, like this. So is it correct? Well, for each mu, we take maximal policy. So when we add, so we add other terms, but all other terms are non-negative by definition of V star. So whatever other policy we use, the reward from mu cannot be bigger. Okay. So our plan will be to use linearity in mu. Okay, so now comes an inequality that needs some explanations, but I will write it first. And so we will have that this mu in M is W mu, P star mu, H smaller than N, minus V mu pi psi, not psi. So here we will replace pi xi by optimal, so by our policy that's self-optimizing. And so note that here we assume there exists one self-optimizing policy, and here we replace it, this pi. So, but we will not need to check that this is a valid inequality. Okay. And then what was I'm doing here? I wanted to have new probability of course. That's what we need to prove. And so the last step is to say that with mu pi probability, mu pi probability 1, this goes to 0. And we also have that this is at least, okay, it doesn't matter if it goes to, yeah. So this is at least 0. Okay. And so this implies the proof. And so if the right hand is 0 with probability 1, then this must be 0 with probability 1 as well. And so that finishes the proof. And so we have to do two things: deal with this inequality and also prove that for this thing, it goes to 0. But it's kind of logical. We know that for each mu separately, this goes to 0 by definition of self-optimizing. Where is it? Here, it's self-optimizing. So it's logical. We just have to deal with the linear combination here. But technically, this is many pages in the book, but I will tell a simple proof. But here is where real magic is. This is just some mathematical issues here. Okay, so what do we need to prove? But it's not so difficult. So no panic. The worst of the lecture is long ago past. So to get this inequality, we need to prove that sum over mu n. So we only the right term, the negative term changes. So here we have pi psi of h smaller n. So so we need to prove that this is bigger. So the other inequality, because it's negative, then sum over w mu r. So sum over mu in the model, of course. Sum over mu in the model of w mu, and here is our special self-optimizing part, which is smaller than n. Okay. So that's what we need to prove. Okay, I was not tactical, so I need to write something in the middle. But note what we are doing here. Yeah, so we are taking the value according to nu. And note that value, our value function is linear when we take linear combinations. So we had this exercise, what happens when we take linear combinations? So here we do the opposite. We have linear combinations of value functions. So this is equal to, so I claim that this is equal to the psi of pi psi. Yes, it is our exercise. We understood it. Psi is linear combination of this double line thing. We talked very long about it. And now we get the fruits of it. So we know that this is bounded by v psi. By definition of optimal function pi psi, this is better than when we plug in self-optimizing function, sorry, other inequality. So it's bigger than this of h. So arguments are always the same. And now we expand again to the sum. So it's equal to sum over W mu V mu by H smaller than N. Okay, and that's what we needed, so that this is bigger than this thing here. That's why this inequality holds. So this bigger than this thing here. So we proved this inequality. And so now the only place of doubt is some mathematical convergence result. So now we will think about analysis. Okay, I will delete this. So, and here is lemma. Let me write it. It's a bit boring. So we start with, the statement of the lemma. So we consider for every nu, we consider functions h, length of nu, and we assume that these are bounded. And we also assume, let me write it here. So delta nu is bounded. So the idea is that delta nu will be the difference of two functions. And we also know that for all nu, this function converges to 0 with nu pi tilde probability 1 for n go to infinity. And so then, if delta is unbounded and this goes to 0, and then the claim is that sum over W nu, and here we use this special measure again. So we have this mu, so here we have E bounded by N. That's right, smaller than N. Given the action smaller than N, divided by psi, E smaller than N, actions on N goes to 0. So here open all the models with mu pi tilde probability 1. So when N goes to infinity. And I forgot to multiply by delta. Okay, I need to write the last one again. So delta mu H goes to 0, right? And mu pi tilde probability 1. And it goes to infinity. So this is the lemma. And so how do we get this thing here from the lemma? Well, we just set delta of H equal to this difference of value functions. So that's the remaining technical part we have to prove. After we prove lemma, our proof is complete. It's a really weird proof, so I keep reading it all the time, and because there's very little is happening in this proof. So how can it be? Tell you that data compress random programs, we should generate random programs and let them guess things. So okay, yes. So yeah, I can repeat all the steps. So what did we use? So first inequality is just adding positive things, nothing happens. Second inequality is this just rewriting and just saying that when we optimize according to Xi, we take all possible environments into account. Then we say that our this single policy that self-optimizes exists. And then we use the self-optimizing policy to get some convergence result. So there is this other policy that goes to 0, and this forces this policy to go to all these policies go to 0. So nothing happens, but still a powerful result. And Marcus Sutter, right? This is the most important result of the book, but I also think so. But and it's very interesting. But how can so little happen in the proof? Okay. So now let's finish the work by proving the lemma. So what is happening here in the lemma? So what's our problem? And so we have here we have a bunch a sequence, but here we are changing from, so we know that H delta goes to 0, but we change the probability here, so we get a different mu. And also a second problem is that we take infinite sum, so maybe each sequence will go to 0. But how do we know that the sum goes to 0? Maybe for some mu, it will go to 0 extremely slow. And what is helping us is that here we have something that is guaranteed to be bounded. So, well, now I'm confused myself. So, something is bound. Okay, so okay, but the proof is not hard anyway. So, so we know that each mu. Okay, I understand again. So proof is as follows. We will consider two types of mu. We consider mu with large weights. And so for every epsilon, we have to prove, where is my definition of convergence with probability 1? I deleted it. I just deleted it, I'm afraid. Okay, so what we have to prove? For each epsilon, we have to prove that probability that for large enough n, that this thing is bigger than epsilon goes to 0. So let me write it. So for each epsilon bigger than 0, we need that limit n to infinity, that probability that this thing sum over and m w mu, the ratio of mu and psi, mu and psi delta mu bigger than epsilon. Okay, I should take absolute value. Okay, let's say delta bigger than 0. Then I don't need to write epsilon, right? It doesn't matter. I can write absolute values. So this should be equal to 0. Okay, so you give me epsilon, and I need to give you big enough n so that this probability is smaller than epsilon. So let us first select weights. So M1 contains enough weights, finite set of weights whose weights sum up to 1. M1 finite. So our plan is, let's make a finite set that contains all but epsilon of the weights. Finite, and sum W mu in M1 is bigger than 1 minus epsilon. Or let's say a mu not in M1 is smaller than epsilon. So now we will use that delta is bounded, and here is some coefficient that's smaller than 1. So when we look to the mu's that are not in M1, they contribute at most epsilon to the sum. And so now for the other ones, I will take individual limit. And so we know that this delta goes to 0. And here is something bounded by 1. So so for the first epsilon in this probability, so we need to make this. So there exists n, so that this is smaller than 2 epsilon. So this is what we want to say. So we can do it for each epsilon, and so we will use 1 epsilon where we just bound the coefficients, and then we use another epsilon when the coefficients are big for those nu and n, we will choose the n large enough so that this delta is small. But there is a small problem. We have new probability, but we only know that we get the new probability of say delta small. It's slightly different. But it's no problem because we multiply by a ratio of measures here. So let us do small exercise. So let us look to expected value of some function f, and let us take probability vector p. So we have some vector y, and we take y from some probability vector p. And imagine that we're not interested in expected value of y, but we use we multiply by ratio of two probabilities here. Then I claim that this is exactly equal to y when we take q probability. So q is also probability vector, q and p. This is exactly equal to expected value of f of y. So there is a question, so where is this ratio here of both measures? I will explain in a second. So the connection with this and this is not yet clear. It has to do with this condition H here. So it's another thing I need to explain. But now I started with the lemma and proving it. So let us continue with that one. Okay. So that's the idea that we will use. Here we have ratio of probabilities. And here we take expected value of, so in our assumption, delta goes to 0 with nu pi probability. So here we have actions, observations and rewards given actions. And here the same, with the double bar. Actions and double bar rewards. Okay. So we know that psi is bigger than nu. So if we prove it for nu, we are already good. And so for the nus who are not in M1, we need here to be psi. But for those who are in M1, we will prove a harder result. We will look to this ratio, but psi replies by nu. So we will prove that probability of well, that's first, since M1 is finite, we can just look to a single one. And so we can just look to mu of E of n given A of n divided by mu E of n, A of n, delta nu of H. Oh, and I need to use strict inequalities. I will explain why we have strict. So we need, because here are strict inequalities. So probability that this is bigger than epsilon, we want it to be bigger than, smaller than epsilon. So if we find n large enough such that this is true, then we take the maximal over all the M1 of such n in the set, and then we are good. Because there is this weight, and then we have that the weighted version is bigger than epsilon is also smaller than epsilon. Yeah. Okay, sorry, we should here we should take a little bit more. We need W nu times epsilon. So that if we take union bound, it's okay. Yes, but now probability being bigger than epsilon is smaller than this. That means that since all of this is bounded, okay, sorry. First, I need to say that since all of this is bounded, we are proving that expected value of this thing is smaller than, is arbitrarily small. Okay, I did not do the right steps. So first, I need to go from probability to expected value. Yeah, okay, I understand. So now you're probably lost, I guess. Okay. So I need to restart proof. Okay. And so here we have sum over m. We consider two cases. Mu in M1, the set with big coefficients, and the other m's. So we will both both sums will be bounded by epsilon. So we need to prove that probability that this is bigger than epsilon is smaller than epsilon. So we will have a probability smaller than 2 epsilon. Probability epsilon will be used for use not in M. So that this remains the same. So now I can restrict to M1. We just need to bound this thing for measures in M1. Okay, so I need to say that probability that this is big is smaller than epsilon. So I will prove that expected value of the sum is smaller, is arbitrarily small. If expected value is small, then probability that this is big is also small by Markov bound. I just need this to prove that this expected value goes to 0. Let's write it like this. So it's equal to 0 when I take limit. Sorry, expected value of this goes to 0 when I take it. So there is no epsilon anymore, which is very convenient. So if I prove this for the sum in M1, right? Then I'm good. Okay. So now I have that this thing here is bounded. So here there is a h smaller than n. Okay, this thing is bounded. And just continue because it don't work. Yeah, I don't know why I'm restarted because now everything is clear to me. So let's continue. So now let us replace psi by mu, because mu is smaller up to a constant factor. And because we defined that psi as mixture here. So it's enough to prove that mu here it is smaller. Okay. So now let us prove that limit of expected value of each term goes to 0 in the sum without the mu here. And this is kind of easy because now I have expected values here. Value. So where we generate, so we have mu by tilde. So we generate according to mu by tilde and so what is the measure here? But here is no. So I somehow. Where is my pulse? Here by tilde. Where I wrote, yeah, the mu by AH from mu by tilde. Okay. And now I apply the same trick as we applied here. And so in the conditional probabilities, when we generate observation reward pairs in the bottom, sorry. So we have observation reward pairs, but we divide by the probability. It's also discrete probability because we have observation reward pairs of finite string. So for each n, we can replace the new probability by the new probability. So this is equal to expected value, but now from h drawn from u, expected value, but h drawn from mu pi tilde, mu and pi tilde. Was it pi tilde and mu? Okay, so mix it here. Pi tilde and mu. Of the same of delta. Okay. And so note that there is a limit I didn't write. So for each such term, we can find an n for which, for each such term, the limit goes to 0. So a finite set, sum of finitely many such terms, also goes to 0. And this is precisely, so we've rewritten the sum to something that goes to 0. And we can do it because M1 is finite. So the problem is that the whole problem in the proof is that this is no longer unbounded. So when we flip the probabilities, we understand it's no longer unbounded. So we have to be careful. But fortunately, this is enough to consider finitely many cases. Okay, and this is 2 papers and some part of a chapter, blah, blah, blah. It's about this technical lemma. I didn't explain it very well, but I will write it in the notes. So if you want to read it. So by the way, there is colloquium, but I will give the main steps on the page. So I will make it. I don't know if somebody took statistical learning theory or something. I will use same system. So you don't need to remember much, just all the steps try to understand. And as I promised, I feel really guilty about teaching too difficult stuff with low quality, the lectures low quality, but I think the lecture notes are more or less okay. But you need extra time to learn it. So I definitely understand this. So everyone who understands a little, a tiny fraction will get at least 7 out of 10 and 8 out of 10, because I know that what happened is not okay, but I will do, I insisted on teaching this proof anyway. So because that's craziness, so that there is something magical happening, I should find a way to teach it. And the first year it's disaster, especially if the world doesn't cooperate. Okay, but there is still a little part. So we understand the lemma. And so the question is, what is the strange factor here? So we understand what is delta, and we understand where this W nu comes from. But suddenly, as there is this strange factor, why do we need it? And it comes from the condition in the value functions here. So yeah, it is because I multiplied not with in the proof. I told you a lie. So I took linear combinations, but when we did this exercise, we understood empty history. And so that's why I told you a lie, and these coefficients don't work because of the history. what's happening is that when we already receive certain history, we can still write posterior distribution as linear combination of original distribution, but we have to correct the coefficients. So there are Bayesian updates for the coefficients, and that's why they appear here. So all of these explanations work only, so this translation of W and U, to replace it by Xi, we need the conditional version of Xi. And only then I can use, so here was this magical connection. We said that this is bigger than this value. But for this, we cannot need the initial coefficient. We need posterior coefficients in the Bayesian mixture. And these are exactly these posterior coefficients. So this is normalization factor. And this is just the probability of getting the history. It's very late, so I don't know. It's kind of tricky. I will write it and then I don't know if I should continue explaining it. It will take 5 or 10 minutes to really convince you that these are the coefficients of posterior mixture. But if you already learned this in other course about Bayesian learning or something, it's kind of obvious. So I don't know what's the time. It's 9:15. So okay, so what is this value function? You need to remember the definition. So this value function, it uses conditional measure. We condition the new measure on the history. So now it means that here in this step, in this intermediate step, we use equality with, it's still here. We use this inequality, but here we need kind of coefficients that depend on the history, so that this linear combination still works on posterior when we condition. So now we need to find what are these coefficients W of H of N. And so we need to calculate them and observe that they're exactly this thing. So we have to say what is psi. Let us look to psi of one observation. Let's look to En. So En is observation reward pair when we have certain history N. So it is psi where we have all of the N's given the actions. Yeah, actually, I don't know. It's a tricky place, but and we normalize by. This is a very intuitive way to say that's the posterior mixture that we work with. So we will divide by this thing. Okay, and so, but now it's easy because in the denominator we have precisely the same thing. It's already here. And in the numerator, we can expand. So we write this times sorry, we need to. So here we have the object where we on which we operate for linear combinations. So we can expand this object here. And so here we have precisely what we have here. Sorry, what we have here, and I made some thing with the strict inequalities. Precisely what we have here, except that we have here one more multiplication with conditional distribution on the nth element. But this is because I look to the posterior just for the next sample here. So when we take expectation over just one next observation reward pair, then we just multiply by 1. But here we take a more complex expectation. So in the delta itself is some expectation. And so all the other conditional distributions go here. But okay, I need to clearly write a step for step, and then this will be completely clear. But it's my task to do this in a better way. So I started in the beginning of the lecture, I already mixed up these double bar things. So it's a challenge, but when everything is clear, so I hope that if you read that the notes will soon be ready and that you read them, this should be clear. There should be no problem here. So it has to do with what do we use this psi for? We use it for predicting the future, but we just normalize by this thing. So that's why we have only one extra n here, because I took an example. What we need here is a measure for arbitrarily z here. So arbitrary extensions, or arbitrary strings of z in observation reward pairs. And so then we have to look here to c multiplied by e over n. So that's the object we need, because this is used inside expectation defining the value functions. So this is used inside. So the part, so when we expand the sum here, we have w nu times mu of ez e smaller than n divided by this normalization. Okay, and then we are at the level of individual mu, and then we can expand the definition of mu. That's what's happening here. So we can write as a product of u of z conditional on events smaller than n times the nu of n. And then this factor nu of n appears here and the psi appears here. So this is kind of intuitive explanation. But again, I will write it clearly, the story from beginning till end, because it's kind of tricky to listen to. Okay, and now you know all the steps individually of the proof. So proof was easier than all the definitions. But it's a rare case where this happens, and I think still the theorem is interesting. And nobody in the world seems to know about it, except some people in DeepMind and now some people in Moscow. So even Vereshchagin doesn't know. I will try to teach at some point to him. Okay. Well, I am not sure. I didn't ask him, but I'm 99% sure he doesn't know. Okay. So now it is 8 minutes before 9. So there is so we didn't solve 4.1 and 4.4, but we can use it for homework. So I will move it to the homework. And of course, I will double check. So 4.4 is just a modification here. So the question is, what if in mu there is just one measure for which our self-optimizing pi doesn't work? So we have almost self-optimizing. Here is definition, but here for all except one measure, it doesn't work. So what can we still say about our mixture measure? And it turns out that that now it's only guaranteed to work on those measures nu, and so pi only works on those measures nu that have large weight. So that's what the exercise says. So everything is destroyed somehow, except for those with large weight. Okay, and the first exercise is kind of tricky to reformulate. So I will read it a few more times. Okay, and now you survived the 4 hardest lectures of the course. Yeah. So everything next will be easy. Just Kolmogorov complexity, proof of at most 15 minutes, all the definitions followed by no more measures, no more probability. I mean, Kolmogorov wanted to get rid of probability, but here it's full of probability. So the
Ask you a question about seminar 2.
yeah.
We discussed semi-computable real numbers.
Yeah.
I don't remember.
The definition, I said supremum as innumerable set of rational numbers.
Yes,
I will take some space.
I don't remember. Have we discussed what is the set of
Rational numbers. So
set of semi-computable real numbers?
yeah. So only in the lectures it does not appear. But so it's defined, but in the seminar it's defined as a supremum of S. And so S is a subset of Q and S is enumerable. So that means that there exists a machine and it gets rational numbers, so pair of integers. And then if it's in the set, the machine stops, and otherwise it keeps running forever. And so that is enumerable set of rational numbers.
Yes, and I wanted to ask you.
Now we're saying computable. And this is that.
I wanted to ask you, are there any algebraic or maybe number theoretic descriptions of long semi-computable numbers?
So I gave a characterization. So if R is well, all algebraic numbers are computable and thus lower semi-computable. So all the computable numbers are lower semi-computable.
What do you mean by what's that?
By computable number, it means that you give a precision and then you compute estimate within this precision of the number.
But that's not obvious definition, because
so
we have a definition about computable real functions.
Functions. So you can say a number is computable if the constant function equal to this number is computable.
But if we have a constant, real constant, why not all real numbers computable?
Okay, a random number is not computable, random real number. For example, binary expansion is infinite bit sequence and it's random infinite bit sequence, uniformly random. So if I flip infinitely many coins, you cannot compute it. So set of computable numbers or set of enumerable numbers is countable because number of Turing machines is countable.
Yes,
Yeah.
that it is obvious that there are not lower computable numbers because no of its definitions. Okay,
Yeah.
but the first question is algebraic numbers are lower
computable. Yeah. And so it's because they are computable. So let me say why computable number is lower semi-computable.
It's maybe obvious too. I want to ask you what we know about more numbers that are lower semi-computable. Maybe there are a lot of numbers that are not algebraic and they are also lower semi-computable. Or
Yeah.
okay, we can use fractions for
but it's the same for computable. So like pi famous number 3.1415 and so on. It is not algebraic. I think there is proof of it. It's proven now, or maybe dispute, or so. At least everyone believes it's not algebraic. But you can compute to any precision you want because that's how they used to test CPUs to test performance of processor or yeah.
maybe there are continuous fractions.
Yeah.
And can you say that computed?
So they're all computable because you can say well, I'm not sure, but I assume they're all computable.
And what they actually meant was that all real numbers can be presented as continuous fractions.
Iterated fraction, yeah.
Maybe.
Yeah, but then you
is
need to calculate the iterated fraction if you want to use it as a method for
continuous fraction is an infinite sequence of
So
naturals.
Yeah, there are one plus and then one divided. So or a one.
Yes.
Something
A1,
like
A2.
this, and here is A0 and A2 and so on. Yeah, but the problem is that here you have sequence of integers.
Yes, maybe the set of lower computable numbers is the set such that we can Turing machine can output infinite sequences of natural numbers. Maybe this set is just the set of continuous fractions such that this sequence can be printed by any Turing machine.
Okay, so you need non-decreasing function, approximation by non-decreasing function. So if you can somehow get it by condition on the sequence, so what happens if I make A2 larger? So if I make A1 larger, then the ratio decreases. So I can decide to make this fraction larger by making choosing A2 small. But then if I choose A3 small plus something here, I choose A3 small, so then this becomes bigger. So this becomes smaller. So it's so yeah.
I just wanted to say that maybe we can describe all lower computable numbers by continuous fractions.
Yeah, so I think if you want limit computable, maybe a better chance. So that means that there is a function. And so limit computable means that there is one way to define lower semi-computable was to have function of it is a limit of function ft for t going to plus infinity. So R is semi-computable if we have non-decreasing function. That's limit. But then there is limit computable. It means that there exists computable function, but no condition on increasing or decreasing. Just it needs to have limit. So number is computable if it's the limit of some computable function. And then I think it might work, but you need to check. So you can say a number is limit computable if there exists a computable sequence of numbers a1, a2, and so on. That
That's what I wanted to say. That there are infinite sequences of natural numbers that can't be output of any finite Turing machine. Yeah, and maybe number R is not lowest incomputable if and only if these sequences of its continuous fractional representation cannot be an output of any Turing machine. Maybe you didn't think about it.
No, not at all. I didn't think about it. You're right. Yeah, I know that friend of me was reviewing paper with such ideas to connect iterated fraction and computability, but long time ago. So some Indian guy wrote something about it, but I think it was different question. It was very special. It was a much weaker class. He tried to model very weak form of computability with iterated fraction. And then but his goal was to solve some mathematical question. So yeah, but I don't know what is the connection. It's a good question. So so you say that, but you should say it again. I didn't completely get it. So you say number is not computable. Yeah. Yeah, to write, I write. Let's make some space.
That's not really correct.
Okay. Yeah.
We should. Is one. Here is a0.
Okay.
It is it's needed to
to have all the all real numbers.
Integer part, and this is lower than even one. This. So what I wanted to say that there are, if this representation
is not possible, then it's not computable. I think.
No.
Ah.
Just real number can be. Oh, so that is maybe obvious, and there is no interesting.
Yeah, so if you can compute a sequence, then you can compute real number. So
yes.
This is not interesting.
Yes, but
opposite.
If we
cannot find sequence, can we conclude it's not computable? It's it's harder question. I don't know.
I thought.
I also didn't think about this question. If you are it's computable. But I think it's also some generally known. So if number is computable, you can get it in any precision. And I think that in the fractions, you can enforce converging precision, or it's not wrong.
Sorry, could you repeat?
So what happens I think that there is fixed procedure. If you get, for example, binary expansion of number, then you can form a sequence or decimal expansion.
I think yes.
Yeah, I think too. And so it's equivalent. So it's incomputable if and only if sequence. But I need to check if this is true.
This is. It would be.
No, but wait, it's not so obvious. If the sequence is computable, we don't know how fast this number will converge. Sorry, I said it's obvious and not interesting, but I shouldn't have said this. Because it can happen if all these numbers are so A has to be integer, right?
Yes.
Okay, what happened? And can it be 0? I guess not, because then it's stupid. Then you so it should
Yes,
be
yes,
at
yes.
least 1. Negative is not allowed, I guess. So it has to be positive. So if
A0 can be negative.
but what happens if there are a whole sequence of ones? What happens with the fraction? So imagine I have the all one sequence. How much is the value?
I thought it was a square root of 2 like A1 and A2.
Yeah, then you set you say okay, maybe we have the same thing, so we have yeah, indeed we can check. So alpha. One over something like this we have to solve.
Oh. That is a golden ratio.
Okay, yeah.
Alpha is if
so-
all of these
yeah.
if all these are what?
And what happens if you very deep, you change this a little bit? How will this propagate? So if I add epsilon here, will this change by epsilon or it will change by epsilon squared when all of them are ones? Oh, let me think. So here we have 1. Oh, it will propagate by epsilon. If this is a 1 and I add epsilon here, this will become this will become a constant. So in the case of golden ratio, it will become a constant times epsilon. Oh, and it will oh, you say golden ratio. So so this is quite big. If I add epsilon here.
Sorry, I lost what
Yeah, so what I want to know is that if I change here a little bit. So I just let's look to all the ones here.
yes,
The sequence with all ones, and now very deep I make small computational mistake. I want to know whether this, when I evaluate all the other, when I propagate up and I do a computation exact, will this change negligible or proportional? So here I change, so I have some value calculated, but there is epsilon error. Will then change this result by something proportional to epsilon, and it seems like it is. But I need to. So here we have.
maybe yes, but this is maybe this is not interesting.
No,
But-
it is
but-
interesting because it means that if propagation is constant, then when evaluating the sequence, so it means the sequence is limit computable. So we can try to mimic a limit computable function by iterating through the propagation. And then in a later moment, we can change a small ratio here and get the final result. And if this is true, that you can make errors propagate, then every limit computable function has expansion from computable sequence. But otherwise, it's every computable function has expansion from computable sequence. So I don't know which one it is. Needs to be carefully analyzed if you can like propagate the error.
Okay. So I thought I started thinking about this maybe
Yeah, you should. Yeah,
then half an hour ago
ah,
because I just thought about it. It was interesting. What is the set of
yeah,
computable numbers? And for
Yeah,
me, that was most obvious idea, but
yeah, it's really cool idea. So
Maybe-
maybe you're even the. Yeah, we should ask somebody, old person who knows this, because iterated fraction, it used to be very important a long time ago. So and also old people know a lot about computability theory. So if they can say more, I think. But if they say no, nobody looked at this, then it's very interesting. You should publish something.
there are periodic continuous fractions, and they are roots of quadratic
Equations.
equations. Yeah.
So you say that if you alternate 1, 2, 1, 2, 1, 2, then you get quadratic
Yes,
equations.
yes. That is a theory of, I don't remember the genre of or Lagrange, maybe Lagrange. But it will be cool to describe
Yeah.
this set.
Oh. Yeah. Okay. Thank you for listening to the lecture. So